This video goes through how to calculate speed and shear squared, specifically how they change with depth through the Ekman layer. I've already written the Ekman velocity solution from our notes. So U equals U naught times the exponential of A times Z, cosine of AZ minus pi over 4. The A there is for pi over HE, where HE is our Ekman depth, and that's defined as pi times the square root of 2AZ over F. The AZ is the eddy viscosity, and the F is the Coriolis parameter. The U naught is also defined, that's the square root of 2 times pi times the quantity tau x, that's the wind stress in the x direction, divided by the water density rho, Coriolis parameter F, and the Ekman depth HE, which we've already defined. V is defined in a similar fashion. The only difference is it has a sine instead of a cosine. The speed equals the square root of U squared plus V squared. We can substitute the U expression and the V expression for the Ekman layer into the U squared plus V squared. And that's what's shown on the next line. So we have U naught times e to the AZ, and that whole quantity is squared. In square brackets, we have cosine squared plus sine squared, and the argument inside the cosine and the sine are the same. We can use the trigonometric identity, cosine squared plus sine squared equals 1, to realize everything in that square brackets is 1. That's a great simplification, and it allows us to write u squared plus v squared as u naught times e to the AZ and that whole quantity squared. At this point, we can calculate the speed. It's just the square root of u squared plus v squared, which is u naught times e to the AZ. So speed exponentially decreases from the surface down through the Ekman layer. We can now step through the calculation of shear squared, which is du dz squared plus dv dz squared. The first step is taking the vertical derivative of the u expression, and that gets long, but it's u naught a e to the az cosine az minus pi divided by 4 minus u naught a e to the az sine of az minus pi over 4. We applied the product rule by first taking the derivative of the exponential term, which varies with z, and then taking the derivative of the cosine term. That's why we came up with two terms in du dz. Similarly, dv dz is u naught a e to the az sine az minus pi over 4 plus u naught a e to the az cosine az minus pi over 4. The next step is squaring the du dz expression and then adding it to the squared dv dz expression. And that's on the next line. This gets really long, so instead of writing out the whole cosine and sine functions, I'm just abbreviating them as capital C and capital S. So what we have for shear squared at this point is u naught a e to the az, that whole quantity squared. And then in square brackets, what we have is c minus s squared plus c plus s squared. And we can rewrite that. The quantity inside the brackets, as we expand out those squares, is c squared minus 2cs plus s squared plus c squared plus 2cs plus s squared. And remember, the c stands for cosine and the s stands for sine. But if you look at those mixed terms, the negative 2cs and the plus 2cs, we can see that they cancel out. And so what we're left with inside the square brackets at this point is c squared plus s squared plus c squared plus s squared. But we know from our trigonometric identity that cosine squared plus sine squared equals 1. So actually what we have inside the square brackets is just 1 plus 1, which is 2. So the shear squared is 2 times a squared times u naught squared times e to the 2az. And for that, we can figure that out by putting in what a is, and that's pi over he, where he is the Ekman depth, and also putting in u naught, which is square root of 2 times pi times wind stress tau divided by rho f he. And that's how we find the shear squared. It also varies exponentially with depth, but it has the e to the 2az dependence. That e to the 2az dependence is there because we squared e to the az. And that's all you need to calculate the shear squared, which comes in handy if you want to know the denominator of the gradient Richardson number.